Hi, my name is Michael Pendasis, and welcome to online lesson number 1 in Math 231, Probability and Statistics. This lesson we will be talking about Chapter 3. The last lesson ended with the end of 2.3, Properties of Determinants and Cramer's Rule. That was the last topic that's going to be on the first test. Okay, so this is the start of the material for the second test, and I'm going to talk about the test on Blackboard. Okay. So this lesson is on 3.1, vectors in 2, 3, and n space. Okay. So let's get started. Okay, so first, chapter 3, which is Euclidean vector spaces. Okay, so chapter 3 is on Euclidean vector spaces, and 3.1, like I said, is vectors in 2, 3, and n space. That's the focus of our lesson. So first, a definition of vectors. So vectors are represented in 2 dimensions. This is also 2 dimensions, is also called 2 space for short, or in 3 dimensions. Space. Okay, so vectors are represented in 2 dimensions or 3 dimensions by arrows. Okay, the direction of the arrowhead specifies the direction of the vector. Length of the arrow specifies the vector magnitude. Okay, and so these are also called geometric vectors. Okay, so this is talking about vectors. Okay, the tail of the vector is the initial point. The tip of the vector is the terminal point. Okay, so we have the tail of a vector is the initial point, and the tip of the vector is the terminal point. So here's an example of a vector. So here is the tail, and this is the tip. Right? So the tail is the back part, and the tip is the front. And so the tail is the initial point. So this is the initial point of the vector, and this is the terminal point, the point at the tip of the arrow there. That's the terminal point. Okay? Make sense? Initial point, terminal point. And this is the definition of a vector. Okay? Okay, and in the book, this is figure 3.1.1. So you can look there for that. Okay. Let's keep going. So that's our definition of a vector. Sorry, the board, the weight on the board, and that risks of falling. Okay, so let's keep going. Okay, so we denote vectors in boldface type. So if we have A, B, V, W, X, and so in boldface type is a notation for vectors. Right? And so these are the common letters that are used for vectors: A, B, V, W, and X. And in boldface, that's how you would represent a vector. And scalars, for instance, you might still use A, but now as a scalar: A, K, V, W, and X. In lowercase, italics, and that would be the notation for a scalar, right? Number constant. Okay. Okay. And so, for instance, if we have a vector V like this, if we use this notation here to represent a vector V, this would be a vector with initial point A and terminal point B. And so this arrow would be V, and it would be equal to the vector AB. Initial point A, terminal point B. Okay, and this is figure 3.1.2 in the book. Okay, so vectors with the same length and direction are equivalent. Okay, so this is the definition of equivalent vectors. Okay, vectors with the same length and direction are equivalent. Okay, and so we say that they're equal in this case. We say in this case they're equal. Okay, so in the case where two vectors are equivalent, we say they're equal, and we indicate that by V equals W. Okay, so V equals W is saying two vectors are equal, but it means they're equivalent. It means they have the same length and direction. So for instance, this vector here is equivalent to this vector over here. So I try to do this right. So even though these two vectors are in two different places, even though this vector's here and that vector's there, they have the same length and direction. And so these two vectors, let's say this is vector V and this is vector W, these two vectors have the same length and direction. So even though I wrote the two vectors in two different places, they're equivalent. Okay? Same length, same direction, different places, they're still equal. They're still equivalent. Okay? Okay, let's keep going. Okay, so the board is staying up. Okay, so next is the parallelogram rule for vector addition. Okay, so this is the parallelogram rule for vector addition. So if V and W, so for instance, let's say we have, I'm just going to draw it to explain it. Let's say we have a vector V and W with the same initial point. So here I'm going to write the same initial point. Okay? So V and W have the same initial point, this point right here. Okay? And V and W are in 2 space or 3 space. Okay? So either we have a coordinate system for 2 space, either we have a coordinate system that looks like this, or in 3 space we have a coordinate system that looks like that. Okay? Okay, so these two vectors are either in 2 space or 3 space, and they have the same initial point. Okay. Okay, so then these two vectors V and W form adjacent sides of a parallelogram, right? And so if I draw another copy of vector W here, and another copy of vector V here, then V and W form two adjacent sides of a parallelogram. Okay? So V plus W would be this vector, the one that starts with the same initial point and goes to the opposite end of this parallelogram. That's the vector V plus W, excuse me, sorry. So V plus W I drew here, this is the geometric representation of how to add two vectors. Okay, so this is the geometric way of finding V plus W. Okay, and so that's the geometric way of finding V plus W. Okay, and in the book this is figure 3.1.4 part A. If you want to look at it. Okay, so that's V plus W. Okay, so that's the parallelogram rule for vector addition. The next one is the triangle rule for vector addition. Okay, so the triangle rule for vector addition. And so again, we're going to take a vector V. So we're going to have vectors V and W are in 2 space or 3 space. Okay? Again, 2 space looks something like this. Vectors in that kind of coordinate system. Or 3 space will look something like that, like coordinate system there. Right? And so V and W are both in 2 space or both in 3 space. And so if you have a vector V, and if I take, this is the initial point of V, that's the terminal point of V. If I take a vector W, and I put the initial point of W at the terminal point of V, like this, right? Then, if I take another vector whose initial point is at the vector, this vector V, and the terminal point is at the terminal point of W, then this vector here, that vector is V plus W also. And so this is another way geometrically to find V plus W. And it's called the triangle rule for vector addition. And so this is another geometric way of finding V plus W. Okay? You take a vector V in 2 or 3 space, another vector W in the same space, take the initial point of W, attach it to the terminal point of V, and then you start from the beginning of V and the end of W, and that's V plus W. Okay? So this is another geometric way of finding the sum of 2 vectors. And in the book, this is figure 3.1.4 part B. So one important law that applies to vectors is V plus W is equal to W plus V. So it doesn't matter the order that you add 2 vectors in the same space. So V plus W equals W plus V. This is the first important equation in 3.1. And so this is the commutative law for vector addition. Okay? You don't need to know the name. That's the commutative law for vector addition. Okay, so I'm going to draw a few pictures unrelated to this. Okay, if you take a vector W here and a vector V here, just illustrating what we just did, then you would take, this would be V plus W, right? That would be the opposite ends of the parallelogram, right? So that would be the parallelogram law again. Right now in B, if you take a vector V and a vector W, and then you start from the initial point of V to the terminal point of W, you get V plus W. And so in B, we have the triangle rule. Right? Okay? And they're the same. And so in C, we just see that by using the parallelogram law, defined V plus W, or so using the parallelogram law to find V plus W, or using the triangle rule, we get the exact same V plus W. Okay, so you get the same vector using either law. And so in the book, now this is figure 3.1.4. Okay, parallelogram rule, triangle rule, they both give you the same vector for V plus W. Okay, so now next is vector addition. Viewed as a translation. So vector addition viewed as translation. Okay, so the assumption here is if VW and V plus W are all positioned so their initial points coincide, then the terminal point can be viewed in two ways. One way to look at it is if we take our vector V, and here's the terminal point, the initial terminal point here, this dot here. Now if you do V plus W, one way to look at a terminal point is that you could just move the terminal point by in the direction of vector W and of the same length as W. Okay, so one way is to what you're doing is moving the terminal point of V in the direction of W, the length of W. So that's one way to view finding the point for V plus W. Then the terminal point of V plus W can be viewed in two ways. The terminal point of V plus W here is the terminal point of V moved in the direction of W, the length of W, I circled here. And the second view is the terminal point of V plus W is the point that results when you take the terminal point of W, okay? You take the terminal, so this is vector W, this is the terminal point of W, and you translate in the direction of V of the same length as V. Okay, and you'll end up with the same point, same terminal point for V plus W. So in this view, we're moving the terminal point of W in the direction of V, the length of V. Okay, so we're moving the terminal point of W in the direction of V, the length, also the length of V. Okay, so these are two ways of viewing the terminal point of V plus W. Right, this is the terminal point of V plus W here. This is the terminal point of V plus W there. Right, this is the initial point of V plus W. This is the initial point of V plus W. So actually, sorry, this is V in the same direction. This is V plus W, and then we're going to move W in the direction. I'm just going to draw this picture there, and then that's V. That's W. Okay, now we're going to v, the direction of w, length of w. That's w though, starting at the same initial point, that's v. Okay, so those are two ways to view vector addition as a translation. Okay, so now vector subtraction. Okay, so for vector subtraction, first let's say that the definition, the negative of a vector v is a vector negative v, such that is a vector negative v with the opposite direction of the same magnitude. That's v. Okay, so the negative of a vector v, the negative of a vector v is a vector negative v with opposite direction and so the same magnitude as v. And so an example of negative v, if you have a vector v here, then it has a certain magnitude, just take the opposite direction and of the same length. So go here. Okay, and so this vector has this is negative v. So negative v is opposite direction, same magnitude. So that's the negative of a vector. Okay, the difference. So the difference of v from w denoted w minus v is the sum. So is the sum w minus v is equal to w plus negative v. And so what we're doing here is we're getting subtraction from addition. So we're building on addition and we're getting subtraction. Okay, so w minus v equals w plus negative v. Okay, and so now that we've defined the negative of a vector, we can now add the negatives of vectors. And so when you subtract a vector, you're adding its negative. Okay. Okay. So that's the definition of vector subtraction. Okay. So let's talk about scalar multiplication. Okay, so scalar multiplication. So if v is a non-zero vector in 2 space or 3 space, and if k is non-zero as a scalar, then we define the scalar product of v by k to be the vector whose length is the absolute value of k times the length of v. And whose direction is the same as v if k is positive and opposite to that of v if k is negative. So this is the scalar product of v by k. So if v is a non-zero vector in 2 space or 3 space, and if k is a non-zero scalar, then we define the scalar product of v by k to be the vector whose length is the absolute value of k times the length of v, and whose direction is the same as v if k is positive and opposite to that of v if k is negative. Okay, so that's the definition. Okay, if k equals 0 or v is equal to 0, then we define kv to equal 0. Okay, so if k is 0 or v is 0, then kv is equal to 0. If that doesn't happen, that means they're both non-zero. Okay, so that means k is not 0 and v is not 0, and then kv, you'll get a non-zero vector described from that definition. Okay, and now equation 3 is negative 1v is equal to negative v. Okay, so that's the third important equation in 3.1. That negative 1 times v is equal to negative v. Okay, so the vector that's opposite the direction of v, of the same magnitude, is negative 1 times the original vector. Okay, or negative 1 times the original vector is opposite direction of the same magnitude. Okay, and so that is the definition of scalar multiplication. Okay, and examples. Okay, so examples of this are if you have the vector v, you have the vector 1/2 v. So 1/2 v is just the vector v, half its magnitude, same direction. Negative 1v is just, you take the same vector, but you just reverse the direction of it. Same. You just reverse the opposite direction, same magnitude. And then if you have 2v, then it's just the same vector, but just double its magnitude. Same direction, double the magnitude. And then if you go negative 3v, it's just the opposite direction of v and 3 times its magnitude. Okay, and so those are 5 examples of scalar multiplication. Okay, of a vector by a scalar. Okay, this is figure 3.1.7 in the book. Okay, so let's suppose VW are vectors in 2 space or 3 space. Okay, so they're both in 2 space or they're both in 3 space, right? They're both in a Cartesian coordinate system that looks like that, or they're both in a Cartesian coordinate system that looks like that. Okay, and they have the same initial point. VW have the same initial point. Okay, so V and W have the same initial point. Okay, if one of the vectors, if one vector is a scalar multiple of the other, then V and W are on the same line. And what that means is that they're collinear. Okay, so if one vector is a scalar multiple of the other, then v and w are in the same line. They're collinear. So an example of that would be if you have a vector v here, and then let's say you have 3v here, then v and 3v are collinear. They lie on the same line. If you have a vector v here, let's say we have a vector 2v here, and then we have a vector let's say negative 7v here, then these two vectors are also scalar multiples of each other, because this vector is negative 7/2 times that vector. And so these two vectors are also scalar multiples of each other. And so if that happens, then this statement says that v and w are on the same line. And that's true. 2v and negative 7v are both on the same line. So they're both collinear. Okay, so parallel lines are collinear. Okay, which sounds weird, right? Because parallel lines, you don't normally think of them as lying in the same line. But look, so if you have a vector v here, and you have a vector w here, they don't have to be the same length. These two lines are, parallel, sorry. So I talked about lines. What I want to I'll just get to the point. And just say parallel vectors are collinear. So these two vectors v and w are parallel, right? They're the same direction. But you can say they're collinear because, remember, moving a vector doesn't change the vector. We say a vector is equal to another vector if it has the same magnitude direction, you just move it. So if I just move v here, it's still considered the same vector. And now it's on the same line. So if I move vector v so that it overlaps w, then the vector v here, that vector v now lies on the same line as w. And so they have the same magnitude and direction, and so parallel lines are collinear. Okay, and note, the zero vector is parallel to all vectors. Okay, so the zero vector is parallel to all vectors. That's because the zero vector is a point, but it has zero magnitude, but it has any direction. So you can give the zero vector any direction you want. And so if you take any given vector v, then you can take the zero vector, which I'm just going to denote as a point. So we have our vector v here and a point here, which is a zero vector, which is zero magnitude. I can assign this vector 0 to be in the same direction as v, and then they're parallel vectors, and they're also collinear. Okay? So the zero vector is parallel to all vectors. Okay, let's keep going. Okay, so there's also this equation that holds. So u plus v plus w is equal to u plus v plus w. And this is called the associative law for the addition of vectors. Okay, so this is the associative law for addition of vectors. U plus v plus w is equal to u plus v plus w. And this is for every u, v, and w. Every vector is u, v, and w. Okay, associative law for addition of scalars. Okay. And so now if you look at the adding of 3 or more vectors, you can use the tip-to-tail method. And it's very simple. So this is a geometric way to add a bunch of vectors. Okay, so let's say you have the vector u here, and the vector v here, and the vector w there. So we take vector u, and we take the terminal point of u and attach it to the initial point of v. Then we take the terminal point of v and we attach the initial point of w to that. Then where we start to where we end, that's the vector u plus v plus w. Okay? And the order doesn't matter. So if we change the order by the associative law, we would get the exact same vector u plus v plus w. And so that's the tip to tail method and applying to 3 vectors, but you can apply it to any number of vectors. So for instance here, we have a vector u here, and then you add the vector v like that, and then you add the vector w there, and then you add the vector x here. Then starting from the beginning to the end, the vector you get is u plus v plus w plus x. So u plus v plus w, u plus v plus w plus x is that vector. And okay, so now that's applying the tip to tail method for 4 vectors, finding the sum. Okay, so now we get u, v, and w. And you can kind of think of, in this example, as u, v, and w being sort of like one edge of like a cube or rectangular prism. And so now adding u plus v plus w, you would get this. And so now this vector would be u plus v plus w. And it would be the end, it would be the opposite end of this box. Right? Okay, so u plus v plus w is the thing that goes from one end of the box to the opposite end of the box. One corner of the box, the opposite corner of the box. That's u plus v plus w. So this is the tip to tail method applied to 3 vectors here, 4 vectors here, and 3 vectors there. In the book, this is figure 3.1.9. This is part A, this is part B, and this is part C. Okay, so let's say we take a vector with n coordinates, v1, v2, v3, dot, 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 vn. This is our vector v, okay? Where each of these are the components of v. The first component, the second component, the third component, up to including the last nth component. Okay, so that's our vector v. And this vector v is in n space, right? It's an n-dimensional space. It has n components, okay? That's not quite the reason, but it's a simple example, so that's what's happening. Okay, so we have a vector in n space, and so the coordinates of v are the components of v relative to the coordinate system that it's in. Okay, so we can change the coordinate system, which would change its components. But the coordinates of v, so the coordinates of v are the components of v relative to the coordinate system that it's in. Okay, so what does that mean, right? So I'll call this a definition. Okay, coordinates of v are the components of v relative to the coordinate system. Okay, and so let's say we have v vector v, v1, v2. These are the components of v in 2 space. And then the vector v, which is v1, v2, v3, this is in 3 space. Okay. coordinates, I mean the v1, v2 here, and the v1, v2, v3 here, and the v1 to be in there. Those are the coordinates of v. Okay. Two vectors are equal if and only if their corresponding components are equal. Okay, so the statement two vectors are equal has the same truth value as their corresponding components are equal. So two vectors are equal if and only if their corresponding components are equal, right? And if and only if here, it means that this statement and this statement have the same truth value. Okay, so either two vectors are equal and their corresponding components are equal, or two vectors are not equal and not all of their corresponding components are equal. So what does that mean? So I'm going to write a fact. I think this is a fact here. So an example is two vectors are equal. So let's say the vector v1, comma v2, comma v3 is equal to the vector w1, comma w2, comma w3. That would be the statement that the vector v here, this is vector v, and this, which we'll call vector w, this is the statement that vector v, and this vector w are equal. That's the same, and so actually I'm going to write the meaning of the point here, has the same truth value as, well, so the statement that this vector equals that vector has the same truth value as v1 equals w1, v2 equals w2, and v3 equals w3. Okay, so this vector v here with three components equals this vector w with these three components has the same truth value as the first component of v equals the first component of w, and the second component of v equals the second component of w, and the third component of v equals the third component of w. That's the meaning of corresponding components are equal. Okay, so corresponding components is their first components are equal, their second components are equal, and their third components are equal. Okay? If any one of their corresponding components was not equal, it would be false to say that they are all equal. It would be false that they're equal. They would not be equal. Okay, and so, so that's talking about two vectors that are equal. Okay, good. So another important thing to mention, let's say you're in two space, so you have the x-axis and y-axis, and let's say you have a point v1, comma v2, and you can also think of the vector from the origin, the initial point of the origin, and the terminal point at that point v1, comma v2. Okay, and this is figure 3.1.11. Then the ordered pair v1, comma v2 can be viewed as a point or as a vector. Okay, so the ordered pair v1, comma v2 can be viewed as both a point or as a vector. Well, one or the other. You have to make a choice, but it depends on the problem you're doing, right? So if you want to work with a point, you can think of it as a point. If you're working with vectors, you can think of it as a vector. Okay? There's just two different ways of describing the same thing. Okay. So if P1, P2 denotes a vector with the initial point P1, x1, comma y1, and terminal point P2, x2 comma y2, then the components of P1, P2 are given by this equation. So the vector P1, P2 is equal to the vector whose first component is x2 minus x1, and the second component is y2 minus y1. And so this vector, that's how you describe a vector starting with this initial point and that terminal point. And so this is, that's y2. Okay, and that's equation 4 in 3.1, the fourth important equation. In 3.1, there's actually a lot more of the 4 equation. Okay, so it's equation 4. So now if we have one axis here and the other axis there, the x-axis and y-axis, if this is your point P1, coordinates x1 comma y1, and then let's say we have another point P2, which is x2 comma y2. The vector P1, P2 starts at P1 and ends at P2. So the vector P1, P2 is this vector. Geometrically, you would represent it as a vector that starts at P1 and ends at P2. Okay? And so, this vector is, this is the origin, which is an O. That's not 0, that's an O. So this is OP1, this vector, and this is OP2. Vector that starts at the origin and ends at P2 is this. The vector that starts at O and ends at P1 is that. This is P1, P2. Right? And so y are the components of P1, P2, x2 minus x1, the first component, and y2 minus 1. Second component, that's because in order, the x distance that this vector travels, right? It's starting at x coordinate x1, and it's ending at x coordinate x2. So if the x component of P1 is x1 and the x component of P2 is x2, then the change in x value is x2 minus x1. Right? So what we added to the original first component, we started with the first component of x1 and then we ended up with the first component of x2. And so what we did was we added x2 minus x1 to x1. Makes sense? So if we start at P1 and we have x component x1, if we add this here, x2 minus x1, then what do we get? We get x2. And so by starting with the first component x1 and adding x2 minus x1 to it, we get the new first component x2. So that's why this vector has first component x2 minus x1. And similarly, if we start with the first component of y1, and then then what this vector does is we start at y1 and we end up at y2. Then we have to start with y1, and we have to add the second component of this vector in order to get y2. And so we have to add something to y1. We have to add something to the y component of this to get the y component of that. And so what do we have to add to y1 to get y2? We have to add y2 minus y1. And so the second component of P1, P2 is y2 minus y1. Okay? So if we start with x1, y1, we add this to get x2, and we add this to get y2. Okay, so you can now find the components of a vector P1, P2. Okay, and then similarly, if you have a if you have P1, which is x1, comma y1, comma z1, and you have the point P2 with x2, comma y2, comma z2. If you think the vector P1, P2, right, we're still going from one point to another point. There's still only 2 points. It's just each point has 3 components. So P1, P2 is x2 minus x1, comma y2 minus y1, comma z2 minus z1. So P1, P2 is now that vector with three components. Because if you look at, so if we have we're living in three space, and so if we have a point P1 here, x1, y1, z1, and then we have a point P2 here, let's say. So I'm going to I'll make this easy to visualize with this example. So if we start at P1 and we end at P2, then the vector P1, P2, you're living in three space, P1, P2. Then to get to go from x1 to x2, we have to add x2 minus x1. To go from y1 to y2, we have to add y2 minus y1. To go from z1 to z2, we have to add z2 minus z1. And so the change in x, y, and z values are x2 minus x1, y2 minus y1, and z2 minus z1, respectively. Okay, so those are the components of that vector P1, P2 there. Right? Okay, so to start at x1, we have to add x2 minus x1 to get x2. If you start at y1, we have to add y2 minus y1 to get y2. And if we start at z1, we have to add z2 minus z1 to get z2. So this is the first component of P1, P2. This is the second component, and that's the third component. Okay, and this is equation 5 in this section. Given these 2 points, P1, P2, the vector P1, P2 is that vector with those 3 points. That's equation 5 and 3 points. Okay, good. So let's look at an example. Example 1. If we have an initial point, so if our initial point is P1, which is 2, negative 1, 4, and if we have a terminal point, and that terminal point is P2 at 7, 5, negative 8, okay, then our vector V, which is P1, P2, is just going to be, right, our formula says it's x2 minus x1, comma, y2 minus y1, comma, z2 minus c1. All right, and so this is x1, this is y1, this is z1, this is x2, this is y2, and this is z2, right? And so the problems you most want to do are once you just plug things in. So now here we go. We have x2, which is 7, minus x1, which is 2, comma, 5 minus negative 1, comma, negative 8 minus 4. Okay? So you just plug in the values of these 6 things into those 6, and then so you get 5, 6, negative 12. So the vector 5, 6, negative 12, that's the vector V, P1, P2. So this is an example of finding P1, P2. A vector starting at a given initial point and ending at a given terminal point. Okay, so we now have our vector V there. Okay, so now another definition. Okay, so the book is calling it definition 1. If n is a positive integer, then an ordered n tuple is a sequence of n real numbers v1, comma v2, comma dot dot dot, comma vn. The set of all ordered n tuples is n space, and it's denoted by R to the n. Okay, so I'm going to box definition 1. I'm going to box this definition. This is important. So if little n is a positive integer, then an ordered n tuple is a sequence of n real numbers, like that. The set of all ordered n tuples is n space. Okay, so as an example, the vector v, which is 2, 3, 5, 2, 3, 5, 8, this is a 4 tuple. Very simple, right? V is just a sequence of 4 real numbers. First real number, second real number, third real number, fourth real number. So it's just a sequence of 4 real numbers, and so it's a 4 tuple. So that V is a sequence of 4 real numbers, and so it's a 4 tuple. Okay? A sequence, remember, is an ordered list. So to explain a sequence again, so we'll allow for finite sequences. So to explain a sequence, right, if you went to the grocery store and first you bought an apple, and then second you bought a pear, and then third you bought peanut butter, this would be a sequence. There's an ordered list of 3 things. This list of 3 things is a sequence. Okay? And so we're talking about sequences of real numbers. And so this is an ordered list of 4 real numbers. And so this list would be, the first thing is 2, the second thing is 3, the third thing is 5, and the fourth thing is 8. Okay? And so in a sequence, order matters. And so if you change the order of your list, you're thinking of a different sequence. And so this grocery list of first you buy apple, second you buy a pear, third you buy peanut butter, if you change that list to 1 is a pear, 2 is peanut butter, and 3 is an apple, then even though you're getting the same things at the grocery store, the order that you get them is different. And so this is a different sequence than that. Okay? So a sequence is defined not just by the things in the list, but the order you put them in. And so this 4 tuple has 4 things in a list. But it being a 4 tuple, right, also depends on the order that you list those 4 things in, right? So if you make if you put a 4 tuple W, which is 3, 2, 8, 5, this is also a 4 tuple, but it's a different 4 tuple, right? The numbers are the same, but you listed them in a different order. Here the first number is 2, there the first number is 3. So right away you already can see it's a different list. And so these are both 4 tuples, but they're a different 4 tuples. So here, little w is a different 4 tuple. Okay, so understanding a sequence is a little bit difficult and a little confusing. Okay, so just trying to explain it there. Okay, so this is an ordered list of 4 things, and so it's a 4 tuple. This is also an ordered list of 4 things. It's also a 4 tuple, but it's a different one because we changed the order of those 4 things. Okay, and actually you could, let's say we had a vector x, you could define vector x as being equal to 2, 2, 2, 2. This is also a 4 tuple, and it's just that you're listing the same thing 4 times. So the first component is 2, the second thing is 2, the third thing is 2, and the fourth thing is 2. And that's allowed, okay? And there would be no difference in rearranging those 2s. You would still get a vector where every component is a 2. Okay. So the vector 2, 2, 2, 2, if you rearrange the 2s, it's still the same vector. The components are still the same. Okay, so definition 2 is vectors v, which is v1, v2, vn, and vectors v and w, which is w1, w2, wn, in Rn are called equivalent or equal V1 equals W1, V2 equals W2, V3 equals W3, dot, 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 Vn equals Wn. Okay? So two vectors in n space, the same n space, are equal or equivalent if their corresponding components are the same. Their first components are the same, and their second components are the same, and the third components are the same, and so forth, to the last one, their nth components are the same. Okay, and so that's the definition of two equivalent or equal vectors in any n space. Okay, and so we indicate this, that they're equal, by v equals w. So v equals w indicates that this vector with n components is equal to that vector with n components. And you don't need to write Euclidean components. You can just denote each of those vectors by a letter and say that those letters are the same. Okay. Okay, so we always want to write things as succinctly as possible. Example 2. A comma B comma C comma D is equal to 1 comma negative 4 comma 2 comma 7 if and only if A is equal to 1, B is equal to negative 4, C is equal to 2, D is equal to 7. Right? And so two vectors are equal if and only if their corresponding components are the same. So their first components are the same, so A equals 1. Their second components are the same, so B equals negative 4. The third components are the same, so C equals 2. And the fourth components are the same, so D equals 7. Okay, definition 3. If the same vector V, V1, V2, dot, 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 Vn, and vector W, which is W1, W2, dot, 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 Wn, are vectors in n space. I'll abbreviate this in the future. Right now I'm going to write all that out. Are vectors in n space, and if k is any scalar, then we define v plus w is equal to v1 plus w1, comma v2 plus w2, comma dot 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 vn plus wn. Okay, and that's equation 10 in this section. Kv is equal to kv1, comma kv2, comma dot dot dot, comma kvn. That's equation 11. Negative v is equal to negative v1, comma negative v2, comma dot dot dot, comma negative vn. And this is equation 12. And w minus v is equal to w plus negative v, which we talked about before. Subtraction is adding the negative of the vector. So w minus v equals w plus negative v. And that's equal to w1 minus v1, comma w2 minus v2, comma dot dot dot, comma wn minus vn. And that's equation 13, this section. And so what we're doing is we're taking the first component of w and adding to it the first component of negative v. And so we're doing w1 plus negative v1. That's w1 minus v1. We're taking the second component of w and adding to it the second component of negative v. And so it's w2 plus negative v2. So w2 plus negative v2 is w2 minus v2. And we continue, so forth. And so this subtraction is defined by the subtraction of real numbers. And so here we're defining subtraction of vectors. Here we're talking about subtraction of real numbers, which is adding the negative of a real number. And so technically, a really technical note, this subtraction is explained differently from that subtraction. Here we're defining the difference of two vectors as w plus the negative of another vector. Here we're trying to define a different, in the past, subtraction of two real numbers is the first number, real number, plus the negative of the other real number. Okay. And so suddenly there's actually two different definitions of subtraction needed for this one equation, which we've already had in the past. Okay. Okay, elementary school. Okay, so okay, so we have these definitions of the sum of two vectors, the scalar multiple of a vector, the negative of a vector, and the subtraction of two vectors. Okay, so you want to take notes on all these things. While even though you're watching a video, you're not in class, and it's in front of you in the video, it's good to write things down still. It'll help you learn it. Okay, so we have these four equations here in definition 3. Okay, so now in example 3, what we have is a vector v, which is 1, comma, negative 3, comma 2, and we have a vector w, which is 4, comma, 2, comma 1. If we do v plus w, so this is following from our last theorem, last definition, v plus w is equal to 1 plus 4, which is 5, negative 3 plus 2, which is negative 1, and 2 plus 1 is 3. Right? So you just add the corresponding components. 2v, you just multiply each component of v by 2, 2, negative 6, 4. And that's 2v. Then, negative w, just taking the negative of the components of w. So negative 4, comma, negative 2, comma, negative 1. And then v minus w is just taking the component of v and adding it to the negative corresponding component of w. And so this is 1 plus negative 4, which is negative 3. This is negative 3 plus negative 2, which is negative 5. This is 2 plus negative 1, which is 1. And this is by definition 3. And so mathematicians usually will reference what they used in order to get the answer to a problem. And so here I'm referencing this solution by saying I did this by definition 3. So I used definition 3 to get the answers to this exam. Okay, so theorem 3.1.1. If u, v, and w are vectors in n space, and if little k and little m are scalars, right? So the notation is that we will use little lowercase letters, lowercase letters for scalars. Then we have these statements. Part A is u plus v equals v plus w. That's the commutative law for vector addition that I wrote before. B is u plus v plus w is equal to u plus v plus w. This is called the associative law for vector addition. Okay, you don't need to know the name. C, this is u plus 0 is equal to 0 plus u is equal to u. And these other ones have names too, but they're not as common, so I won't confuse you by saying them. Okay, so this is u plus 0 equals 0 plus u equals u. What that means is that if you take any vector and add the 0 vector to it, you get the same vector. Okay. D, u plus negative u is equal to 0. And so what this idea is that if you take any vector u, it has a negative u. And if you take a vector u and add this negative, you get 0. Okay? It's like the inverse of negative u is the additive inverse of u. So you take u and add its negative inverse, you get 0. E is k times u plus v is equal to ku plus kv. And so what I did was I had two vectors u and v, and I multiplied on the left by the scalar k. And so k times u plus v equals ku plus kv. Okay, so it's like the distributive law, except you're multiplying the left by a constant. Okay. Now f is k plus m times u, and this is equal to ku plus mu. And so now I'm adding two scalars, two constants, two numbers, k and m, k plus m, and multiplying the right by the vector u. So k plus m times u is equal to ku plus mu. And g is k times mu is equal to k times m first, and then times u. And so we're multiplying the same three things, but the parentheses are changing the order of it, right? And so in math, the purpose of parentheses is to assign an order to your operations, right? So the parentheses are saying first multiply m and u, then k times that product. And here you're multiplying k times m, those two scalars, in parentheses, then you're multiplying by u, right? So in math, we have the order of operations, which means that if you don't write any parentheses, there's a given order to all your operations, right? It's called the order of operations. But then if you want to talk about a different order, you need to use parentheses. So there's a given order, there's like the conventional order of all your operations, and if you want a different order, that's when you use parentheses. And so here we're using parentheses to say, instead of multiplying from left to right, I want to multiply these two things first, and then here I want to multiply those two things first. Okay, h. 1 times u is equal to u. Okay, and so this looks obvious, but there's actually times where this doesn't happen. Okay, so, okay, but in this case it does. Okay, so we're actually, there's actually some built-in assumptions to what we're doing. And so in this situation, which is very common, 1 times u is equal to u. So that's saying if you take a vector and multiply it by the number 1, on the left you get u. Okay, but there is strange situations and very different situations where that can actually not work. So I think it's kind of cool. That can be false. So that has to be a theorem. Okay, so theorem 3.1.1. If u, v, and w are vectors in n space, and if k and m are scalars, then these 8 equations hold. Okay, and so this theorem has a proof, and after the proof is done, it validates these 8 equations. Theorem 1.2.1. Theorem 3.1.2. If little v is a vector in Rn and k is a scalar, so if little v is a vector in Rn and little k is a scalar, then 0 times v is equal to 0. B, k times 0 is equal to 0. And c, negative 1 times v is equal to negative v. Okay, so here's theorem 3.1.2. If little v is a vector in Rn and k is a scalar, then these 3 equations hold. And so this theorem also has a proof. And with that proof, you can say we have these 3 facts. Okay, so, but now I have to explain a little bit more about this. This 0 is a scalar. Okay, so the words I'm writing here are not part of the equation. This 0 here is the scalar 0. It's the number 0. This 0 here is the vector 0. Okay, and so in the context, so what's happening here, if you take the number 0 here and you multiply it by v, then what you're doing is you're multiplying each component of v by 0. And that means you get a vector whose all of its components are 0. And so an example of this, so an example of A would be if you have v, which is v1, comma v2, comma v3, and then you take the number 0, then 0v would be 0 times v1, comma v2, comma v3, and if you multiply each component by 0, you get 0. But now this 0 here, that's this vector. It's the 0 vector with 3 components. But that's okay, because what's happening is if we take a number and we multiply it by a vector, the result is a vector. Okay? And so if we're saying multiplying a number by a vector equals 0, then we know that multiplying a number by a vector gives a vector. And so since the result of this scalar multiplication is a vector, saying it equals 0 means we know it's equal to 0 as a vector. And since v is a vector and Rn is given, we know that there's a vector with n components. And when you multiply a vector with n components by a constant, you get another vector with n components. And so without only writing equals 0, I know that this has to be the 0 vector of n components. And so before, when I said that the best mathematics is the most succinct mathematics, it's better to not say that this 0 is an n component 0 vector. It's better to just write equals 0. Because even though it looks like it's ambiguous, it could be the number 0, the vector 0. We actually know enough from everything else around it to conclude that this has to be the 0 vector with n components. And so more succinctly, by writing nothing as to what we mean by that 0, we actually conclude that it has to be right vector. Okay, so we've said the same amount of information by writing nothing about what that 0 represents. And so that's the best way to write it, equals 0. Okay? Okay, so b, it's the scalar k times 0. And so now here I mean the vector 0 of n components. Okay? And so now k times the vector 0 with n components is another vector with n components, the 0 vector. Okay? And then negative 1 times v is just negative v. And so we talked about that before. Okay? Okay, and so the next thing I want to point out is calculating that components. So x plus a is equal to b, and that's given. And so the goal is going to be to find x. Okay, that's the goal. And we want to do it without finding the components. And so even if we were given the components of a and b, we want to find x without computing components. And so let's apply the laws that we talked about before with vectors to this example. And so if you start with x plus a here, if you start with the left side of this equation and you add negative a to it, that's equal to adding negative a to the right side of the equation also. And so I'm going to take each side of this equation and add negative a on the right to it. Okay, and so that those two sides are still equal. Then, if I change the order of the addition here by associativity, right? The associative property says that instead of doing x plus a plus negative a, I could do x plus a plus negative a. And this is equal to b minus a. Now, one of the other laws said that if I take a vector a and add its negative, a plus negative a is 0. So a plus negative a is 0. So this is x plus the vector 0 equals b minus a. Okay. Another law said that if you take a vector x and add 0 to it, you get the same vector x. And so that's x, and x is equal to b minus a. And so our answer is that x is equal to b minus a without computing the components in any step. Okay. Okay, and so here, this is by theorem 3.1.1. And in this step, in this step, I used associativity. That's part B of that theorem. Then here, I used part D. So saying that a plus negative a is 0, that's part D of the theorem. Okay. And then saying a vector plus 0 is equal to itself, that's part C of the theorem. And so we reach this conclusion by theorem 3.1.1. And so here I just add negative a to both sides on the right side. Then to go from here to here, I use part B of that theorem, and then go from here to here, I use part D, and then go from here to here, I use part C. Okay, and so we accomplished our goal. The goal is to find x. We found x. X equals b minus a. X is b minus a. And so this goal is achieved right here. So definition 4. Okay, so definition 4. If W is a vector in Rn, then W is a linear combination. Then I'm going to say then vector W is a linear combination of, if W is a vector in Rn, then yeah, W is a linear combination of vectors v1, v2, vn is v sub r. I mean v1, v2 to vr in Rn if it can be expressed as W is equal to k1 v1 plus k2 v2 plus dot 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 plus kr vr. 14. And so this is okay. So if W is a vector in n space, then the vector W is a linear combination of these vectors in Rn. If we can write W as being equal to an expression like this. Okay, that's equation 14. Where K1, K2 to KR are scalars. These scalars are the coefficients of the linear combination. Okay, if R is equal to 1, 14 becomes W is equal to K1 V1 plus KR VR. I'm sorry, W is equal to K1 VR. Okay. So a linear combination. Of one vector is a scalar multiple of that vector. Good. So if W is a vector in n space, then vector W is a linear combination of those R vectors in n space if it can be expressed as W is equal to that. Okay? And so these K's, K1 to KR, are the coefficients of that linear combination, right? So here, here, and so forth, and here, those are the coefficients of that linear combination. So this whole thing I squiggly underlined is the linear combination. Things I circled are the coefficients of that linear combination. So coefficients of linear combination, the entire linear combination. Okay? And when R is 1, that means that we're not in, when we add R products here, where R is 1, we only have one product. So W is equal to K1 V1. Okay? And so a linear combination of one vector is a scalar multiple of that vector. So a linear combination of just the vector V1 is just a constant multiple of that vector V1. And so here, this is definition for a linear combination. Okay? Good. Okay. Okay, so vectors in Rn can be written as okay, so V is that vector. So V is that vector there with n components, and it's a vector in n space. And so this is called delimited form. Okay, so this is comma delimited form. This is one way to write a vector, or you can take that same vector and you could write it using a matrix. And so this row vector, v1, v2, dot, 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 vn, here I wrote it as a row in row vector form. Okay, and so this is equation 16 in this section. And then, or another way, you can take that same vector, you can write it as a column vector. So it's v1, v2, dot, 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 vn. And this is column vector form. Okay, and that's equation 17. So this is equation 15, equation 16, equation 17. These are three ways to describe a vector, the same vector v in n space. Comma delimited form, row vector form, column vector form. Okay, and so that is the end of 3.1. Okay, so we finished 3.1 there. Okay, so we've actually gone further than I expected, and so we're going to continue 3.2. Okay, so 3.2, section 3.2 is on the norm, dot product, and distance in Rn. Okay, so 3.2 is on the norm, dot product, and distance in n space. Okay, and so definition 1 in 3.2 is now if v is equal to v1, v2, vn is a vector is in Rn, it's still a vector in Rn, then the norm of v, also called the magnitude of v, also called the magnitude of v, is denoted by this symbol and defined by okay, so in definition 1, if v is this vector of n components, is vector in n space, then the norm of that vector v, whether its magnitude, denoted by that symbol here, which I'm going to circle, that's not part of the notation, I'm just pointing to it. The norm of magnitude of v, this is the square root of the sum of the squares of its components. Okay? And so that's the definition of the norm or magnitude of a vector. Okay, and so it applies the it applies the triangle rule. I mean Pythagorean theorem. Sorry. So example 1. If v is the vector -3, 2, 1 in R3, then the norm of v is equal to the square root of the sum of the squares of its components. And so this is the square root of -3 squared plus 2 squared plus 1 squared. So if you take norm of v, which is the square root of the sum of the squares of its components, we get this, and then this is the square root of 9 plus 4 plus 1, and this is the square root of 14. Okay, and so the norm of v here is, or its magnitude is 14 by definition 1. So if you want, that's by definition 1. Okay. Okay, so theorem 3.2.1. If v is a vector in Rn and k is any scalar, then, so if v is a vector in n space and k is any scalar, then A, the norm of v is greater or equal to 0. B, the norm of v is equal to 0 if and only if, this is if and only if, that's a bijection, that's the biconditional symbol, it's a notation for if and only if, so that's biconditional symbol. Notation for if and only if, so the norm of v is equal to 0 if and only if v is equal to 0, and C, the norm of kv is equal to the absolute value of k times the norm of v. Okay, and so this is theorem 3.2.1, now in section 3.2. If v is a vector in n space and k is any scalar, then the norm of v is greater or equal to 0, the norm of v equals 0 if and only if v is equal to 0. The norm of kv is equal to the absolute value of k times the norm of v. Okay, so let's look at b. What b is saying is that the norm of v is equal to 0 has the same truth value as v is equal to 0. And so given any vector v in n space, we don't need k here for this part b, saying that its norm is 0 has the same truth value saying the vector is 0. And so it's either a vector's norm is 0 and it's 0, or a vector's norm is not 0 and it's not 0. Okay? Okay, and so that's theorem 3.2.1. So since I have some room here, I'm going to write the next definition here. It's a slightly different idea. A vector of norm 1 is called a unit vector. Okay, so a vector of norm 1 is called a unit vector. Okay, and also, if you have a non-zero vector v in n space, then if that's true, that implies that the vector u equals 1 over the norm of v times v defines a unit vector in the same direction as v. Okay? So we have the definition of a unit vector. It's a vector of norm 1. Now, if we have a non-zero vector in n space, then the vector u, which is 1 over the norm of v times v, defines a unit vector in the same direction as v. Okay, so given any non-zero vector in n space, we can talk about a unit vector in the same direction as it by dividing that vector by its norm, its length. Okay, so with that, let's look at an example so that can make more sense. Okay. So a lot of people find that part to be a little bit difficult. It can be simple if you just break it down a little bit. Okay, let's see. Okay, so example 2. Okay, find a vector u with the same direction find a unit vector. Find a unit vector u with the same direction as v is equal to 2, 2, -1. Okay, so we want to find a unit vector u with the same direction as v as that vector. Okay, and so your intuition should tell you that this is possible. Sometimes if you don't have enough information, you can't know everything from a certain, so if somebody gives you just some information, you can't know it. There's things you can deduce from it and there's things you can't, right? But in this example, we know the direction of v, and a unit vector has magnitude 1. And so the vector we want to find, we know that we can find its direction and we know its length. And so we know that we can get both the direction and magnitude of the vector we're trying to find. And so that will determine our vector, right? And so we can see we have enough information to find the answer to this problem. Okay, so, but anyway, from the last thing I just wrote, since v is non-zero in R3, okay, here's in Rn, it's specifically in 3 space because v has 3 components. So V is a non-zero vector in 3 space. It's non-zero because at least one of its components are non-zero. In fact, all of its components are non-zero, and so it's obviously not zero. And so this vector V is non-zero in R3. That implies, from our last statement, that we can define a unit vector U in the same direction as V if we define a new vector U as equaling to 1 over the norm of V times V. Now this vector is, you could also think of it as V divided by the norm of V. These two things are equal. So what we're doing is we're taking our vector V and dividing it by its length. Okay? And so if we start with a vector V of some length in some direction, that's a vector calling it V with this magnitude and that direction, right? Direction, you can think of it as its inclination above the horizontal line. And so that inclination is its direction, and its magnitude is length, right? So this vector has both magnitude and direction. Now if we want to talk about the unit vector associated with this vector, then we want it to be the same direction of length 1. And so if this vector has a certain length, let's say the length, let's say the norm of this vector was 3. Let's say the length of that vector was 3. Well, if I wanted the unit vector in the same direction as V, right, it might intuitively make sense. All I have to do is multiply that vector by 1/3. If I multiply a vector of length 3 by 1/3, it's going to keep the direction it had, but now it's going to be length 1. And so now I'm going to call this vector U, which is 1 over 3 times V. That U is 1/3 V. Okay, the whole thing here is V of length 3, and then U is just multiplying V by 1/3 because its length is 3. And that will keep it in the same direction, but now it'll change the magnitude from 3 to 1. And that's what this equation is saying. I'm just taking U, I'm taking the vector and dividing it by its length. That will keep its magnitude the same. I'm multiplying by 1 over the magnitude of V. I'm multiplying by a constant. I'm keeping the direction the same, but by multiplying it by 1 over the length, or dividing by the length, I'm now changing the length to be 1, and I'm changing nothing else. Okay? Okay, so now in the problem, we want to find the unit vector associated with this vector V. Okay? And so here, U is equal to V divided by the length of V, or 1 over its length time. So here, what is the length of V, right? So a side question is, what is the norm of V, right? We want to find the norm of V so we can multiply V by 1 over its magnitude. So what is the norm of V? So the answer to that is the norm of V, by definition, is the square root of the sum of the squares of its components. So the norm of V is equal to the square root of 2 squared plus 2 squared plus negative 1 squared. 2 squared plus 2 squared plus negative 1 squared, the square root of that sum. And so this is equal to the square root of 4 plus 4 plus 1. That's equal to the square root of 9, which is 3. Okay? And in the definition, we said the norm was the square root of a sum of squares, right? And it's not ambiguous as it's not a plus or minus statement. When you write the square root of something, like the square root of 4, built into that notation is the understanding of which one you're choosing. And so if you wanted the positive square root of 4, you could just write the square root of 4. That would mean the positive square root of 4, which is 2. If I wanted the negative square root of 4, I would actually write the negative symbol in front of the square root of 4. And so the negative square root of 4 would be negative 2. And so never in your notation is there, when you say the square root of 4, you don't mean plus or minus 2. You mean only 2. When you write negative square root of 4, you mean negative 2. And so in mathematics, when you have a certain notation, the best notation is one where it's clearly understood there's only one answer to the question, right? And so the question of what the square root of 4 equals, it only has one answer. It's 2. It's not plus or minus 2. Okay? And so here, in the definition of norm, when it says the norm of V is equal to the square root of something, it's only the positive square root. And so when we get that the norm of V is the square root of 9, it's not plus or minus 3. It's only 3. And that's built into the notation of the square root notation. That if you tell the reader which square root you're talking about by either having a minus sign in front or nothing, which is plus. You could write plus or you could write nothing in front. That means the positive square root, and negative in front means the negative square root. Okay? And so when we get norm of V is equal to square root of 9, writing nothing here means the positive square root of 9, which is 3. And so this is one answer, the norm of V is 3. And so this is 1 over 3 times V. This is 1/3 times vector 2 comma 2 comma negative 1. This is equal to 2/3 comma 2/3 comma negative 1/3. That's our vector U. So u is 2/3, 2/3, negative 1/3. That's the same direction as that vector v, and it's of length 1. As a check, you can check to make sure, check to see that the norm of u of the vector we got was 1. And to do that, just calculate the norm of the vector u we got. It's the square root of the sum of the squares of its components. That's 2/3 squared plus 2/3 squared plus negative 1/3 squared. Okay? And so we're taking the sum of the squares of the components of u, and what we'll see is it's 1, which means its norm is 1. So 2/3 squared is 4/9, plus 2/3 squared is 4/9, plus negative 1/3 squared is 1/9. And so this is the square root of 4/9 plus 4/9 plus 1/9, and that's the square root of 9/9. That's the square root of 1, which is positive 1. So what we showed here in the check is that the norm of u is 1. And by the definition of a unit vector, if the norm of a vector is 1, it's called a unit vector. And so we found a vector with the same direction as v of length. So there we go. We got the answer. Okay. Good. Okay, so we got the answer. Okay, so the unit vectors in the positive direction of each coordinate axis are called the standard unit vectors. Okay, so the unit vectors in the positive direction of each coordinate axis are the standard unit vectors. Okay, so that's a definition. Okay, so if you have this one coordinate axis here, this one here, and this one here, so let's say we're looking at R3, which is the space or set of all three tuples. And so let's say we have the x-axis here, the y-axis here, and the z-axis there. Then what we said are the unit vectors in the positive direction of each coordinate axis. Those are the standard unit vectors. So let's look at one coordinate axis, x. That's a coordinate axis. Okay. Here, x, y, z axes are the coordinate axes. Right, so in case that's confusing. Right, x, y, and z are the coordinate axes, right? Okay, so we want a unit vector in the positive direction of each coordinate axis. So this is the x-axis, this is the positive direction. Just take a unit vector along that axis. And so this is a unit vector, this is of length 1. I'm not calling it 1, I'm saying the length of that vector is 1. This unit vector in the direction of positive direction x-axis, that's one of the standard unit vectors of free space. Now, if you take the unit vector in the direction of the positive y-axis, right, here's the y-axis, here's the positive direction of the y-axis, take the unit vector along that axis, that's another standard unit vector. Now take the unit vector in the positive direction of the z-axis, and that is our last unit vector for this coordinate axis, that's the third standard unit vector. Okay? So in n space, there are n standard unit vectors, and so in 3 space, R3, there are 3 standard unit vectors. There's the unit vector in the positive direction of the x-axis, there's a unit vector in the positive direction of the y-axis, and there's a unit vector in the positive direction of the z-axis. And so 3 axes, so 3 standard unit vectors. Okay, so that's the definition of the standard unit vectors for an n space. Okay. Okay, so then in R2, these vectors are denoted by I, which is 1, 0, and j, which is 0, 1. Okay, so in R2, these vectors are denoted by I, 1, 0, and j, 0, 1. Okay, and so if you have the x-axis here and the y-axis here, then I is the unit vector here in the positive direction of the x-axis. So and the x component is 1, and all the components are 0, so 1 comes 0. Here the unit vector in the positive direction of the y-axis means that the y component is 1, because the unit vector in the positive y direction, but then every other component is 0. And so here j is the point 0, 1. Or the vector 0, 1. Remember, each point in n space you can think of as a vector or as a point. Okay, so those are the standard unit vectors in R2. So the standard unit vectors in R2 are denoted by I and j, and it's 1, 0 and 0, 1 respectively. In R3, the standard unit vectors are denoted by, still talking about standard unit vectors. In R3, the standard unit vectors are denoted by I, which is 1, 0, 0, j, which is 0, 1, 0, and k, which is 0, 0, 1. Okay, and so here, k is that. And so now these three vectors are the standard unit vectors in R3. So if you have your x-axis here, you have your y-axis here, and you have your z-axis here. These are your three core axes for R3. This is one choice of three axes for R3. Then the unit vector in the positive direction of the x-axis here, the unit vector in the positive y-axis, direction of the positive y-axis is that. So now this is the vector where the x component is 1 and all the other components are 0. This is the vector where the y component is 1 and all the other components are 0. This is the vector where the z component is 1 and all the components are 0. And so this is called I, this is called j, and that is called k. And so this I, j, and k for the standard unit vectors for R3. And so even though here I'm saying I is 1, 0, and here I is 1, 0, 0, there's not two different. That's okay because I'm talking about different spaces. Here I'm talking about R2, and so the I associated with R2 is 1, 0. Here the I associated with R3 is 1, 0, 0. And so using the same letter is actually better than using a different letter because the idea is that the first component is a 1 and the rest components are 0. Okay? And so in different space just means there's a different number of zeros for the other components. Okay. Okay, so every vector in Rn, so every vector in n space can be written uniquely as a linear combination so every vector in Rn can be written uniquely as a linear combination of the standard unit vectors by writing this. If you have a vector v, an arbitrary vector v in n space, which is the first component is v1, second component is v2, and the nth component is vn. You have an arbitrary vector v in Rn. You can write this as v1 times the vector 1, 0, 0, dot, 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 0, plus v2 times the vector 0, 1, 0, dot, 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 0, plus dot, 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 plus vn times 0, 0, 0, 1. And so if I split up this one vector as a sum of multiples of these n vectors, right, where the first vector has a 1 in the first component and zeros everywhere else, the second vector has a 1 in the second component and zeros everywhere else, so on. Then the nth vector has a 1 in the nth component and zeros everywhere else. Then this is equal to, this vector is, I'm going to write this as E1. So let me write inside here. E1, I'm going to write equal to 1, 0, 0, dot, 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 0. E2 is equal to 0, 1, 0, 0. So forth. E sub n is going to be zeros everywhere except the last component of 1. And so in this notation, E sub I, E sub a number is that component has a 1 and every other component is 0. So E sub 1, a 1 is in the first component, everywhere else 0. E sub 5 would be 1 in the 5th component of row 0. And so this is equal to v1 e1 plus v2 e2 plus dot 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 plus vn en. And so what I showed was that any vector v in Rn can be written as a linear combination of the standard unit vectors, where these are the standard unit vectors e1 to en, and these are the coefficients for those n standard unit vectors. And so this is the end of this lesson. There'll be a new lesson very soon. Thank you for tuning in, and see you on Wednesday.